Well, what I would like to do today is give you all a brief introduction to an interesting variable star that we've been studying for the past 20 years. And in addition to that, what I'm really hoping to do is interest some of you in joining our research team to help with follow-up observation and preparation. For those of you who are interested in a deeper dive into this star than I can provide in 20 minutes today, I would point you to a paper in the Astrophysical Journal that we just published this past year, which has a very detailed description of the known observational history of the star. So this star was discovered in the MOTES-NAT Sky Survey #1, and for those of you who are familiar with that survey and with time delay integration photometry, this is what the raw light curve looks like. This is obviously 2 seasons of observing, 2001 and 2002. It's clearly a variable star with an amplitude of something on the order of about 0.6 of a magnitude. And this type of morphology in the light curve is very indicative of a likely short period periodic system. In fact, when we apply these data to a Lomscargel periodogram, we find that we get a very nice sinusoidal light curve with a period of about 6.6 days. But one of the issues with the cadence of the MOTES survey is that as we get to shorter periods, we start to run the risk of aliasing the observations. So typically one of the first things we want to do when we see a star like this is go out and spend a few nights on it to see what the period truly is. And in fact, historically, that's been a very interesting project to put forth for students who have a desire to have gratification in a very short period of time. So following that protocol, we put this star on a program of pointed follow-up observation, which was started in 2010. And we had only been in the program for about a week when we were astonished to find this. And so this is an outburst in energy in the light curve. It occurred very close to maximum. It is a very large outburst. We caught only part of it, but it has a duration of at least 4 or 5 hours. And after we got a distance to the star, we determined that the magnitude of the outburst was about 10 to the 37th ergs, which is huge. So it piqued our interest immediately, and we basically dedicated a C14 telescope to daily observation or nightly observation of this star. And this is the phase diagram for the first year of observation. And the important takeaways from this are that it sustains the period of about 6.7 days throughout the year. It's a pretty decent sinusoidal light curve. You can see the huge outburst that got our attention right off the bat. But the other thing that's interesting is that there appears to be quite a lot of sizzling in the light curve, which is certainly quite significant. So after the first year, we continued for 10 more years. And this is a summary of the phased light curves from 2010 to 2020. The takeaways here are that we see quite a number of these outbursts. The most energetic of them that we saw was 10 to the 38th ergs. And the sinusoidal nature of the light curve tends to be sustained throughout the whole period, but with some slight phase shifting in the shape of the curve. You'll notice that some of the minima appear fairly sharp, some of them are more rounded. Some of the ascending or descending legs tend to wobble around a little bit, but the period has been quite stable over the entire run of observations that we've made. The outbursts themselves, the major outbursts, we can look at in a little bit more detail here. If I can get the speaker again. Up. Okay. So these are the 9 largest outbursts seen in a higher time resolution. I don't want to spend a lot of time on these, but there are a couple of things that emerge as of interest here. One is it looks like there might be a couple of morphologies to the outbursts. There's some of them that clearly have a lot of bumpy structure in them. They look almost like beads on a string plowing into something. In fact, I have another light curve of Shoemaker-Levy going into Jupiter that, except for the time scales and the magnitudes, looks very much like some of these outbursts, which was suggestive of a model that we propose later. There are situations where many, not most of these outbursts are not caught in their entirety. We either catch the tail end of one in the morning, or we catch one at the end of the night, or in some cases, they span a night. We see it on one day, and then the following day, we pick up the tail end of it again. So these are the outbursts. Again, this is just the outburst data. So you've got delta magnitude plotted as a function of phase. And boy, we've had a lot of discussion about this. You certainly get the visual impression that there's a bimodal distribution of the outbursts here, and that they tend to cluster around phase 0 and 0.5. There's some argument over whether there's enough data here to achieve any kind of statistical significance, but it really is tantalizing, and is part of the reason that we need collaborators to do some follow-up observation. So by 2017, we were really starting to commit a lot of our time to this star. And that included hours and hours of discussions, mostly led by Roy Tucker, who many of you will remember. And by 2017, we had some 30,000 photometric observations in June. We felt like we were hitting the wall on what we were able to learn from the photometry. But there were these huge outstanding questions. Isn't it Eclipsing binary? If so, what's the period? Is it 13.2 days? Is it a spotted rotator? Is it a pulsator? What were the sources of outbursts? Are they really correlated to phase, or is that just a coincidence here? We needed some information on stellar classification and evolutionary state of the star. So there were a lot of fundamental questions unanswered, and it was pretty clear to all of us by that time that we really had to get a spectrograph. And in fact, we had already done some spectroscopy with just some little windows of opportunity that we had on the Bach 90-inch telescope at the 50 observing station at Stewart Observatory. We used the Bohlin-Schiven spectrograph there and produced spectra that looked like this. So there were several takeaways from these initial spectra. They weren't as good as we would have liked, but we clearly see H-alpha strongly in emission. The shape of the spectrum seemed very much like an early K star, and it seemed pretty apparent at that point that this was a single star. So with those data, we had a K3 type single star, chromospherically active in most likelihood, of unknown luminosity. By 2018, And on into 2020, we started doing spectroscopy at the Mount Graham International Observatory at the Vatican Advanced Technology Telescope. And that's the spectrograph on the left there. And in 2018, we experimented with doing spectra in both the red and the blue. As an aside, I will notice, reminiscent of the talk we heard yesterday, that in point of fact, we don't like to do spectroscopy without doing simultaneous spectrometry. And you can only imagine the amount of remaining hair I would tear out if it turned out that we missed awareness of an outburst during the spectroscopic observations. Now, as it turns out, there was no such outburst, but we do coordinated photometry with one of our team members, Andy Kuleza, who operates this station in Adelaide, Australia. So this is one of the spectra from 2018. This is a blue spectrum. You'll notice that it's bounded on the left by calcium, H and K, and on the right by the magnesium triplet. The H and K lines are interesting. If you look at them carefully, and that's the inset up on the upper left, they exhibit a p-sigma profile, and they have an emission reversal in the absorption curve, all of which is highly indicative of chromospheric activity. If we look at the red region of the spectrum, we see that on the blue end, we're overlapping the magnesium-1 triplet, and on the red end, we have H-alpha. We also have sodium D lines in absorption. So using the blue spectra from the 2018 one, one of our team members, Chris Corbley, provided this tentative spectral classification. And we did have a spectral energy distribution that allowed us to arrive at a temperature of about 3950 Kelvin. I think that the spectrum itself is best characterized by Chris's comment here. He says MG1-688432 is not like any normal star, single or composite. It varies night to night and never matches an NK standard particularly well. And in fact, if you study the spectra a little bit more carefully, you can see many of these changes. This is from a paper that I referred you to earlier. The four spectra in the center are our target star from April 2018. It's bounded on the top by Alpha Arri, which is a K1 giant, and on the bottom by HR 753, which is a K3 dwarf. And if you study those spectra, you will see many, many variations in detail of the spectrum. The red spectra that we obtained in 2020, we used to produce a radial velocity curve. And that was an interesting exercise. We had a 7-night observing run, 2 nights lost to snow. 5 nights were good. We got an average of about 10 or 12 spectra per night. And so each of these data points represents the weighted mean average of about 10 spectra obtained on that night. And you can see that we can put a pretty nice sinusoidal fit through those, which gives us a systemic velocity of about 34 kilometers per second away from us, and it's an orbital velocity of about 30 kilometers per second with a sin I on mean. So now the situation had changed with the arrival of spectroscopic data, and we did gain some insights from it. First thing that we found that was important is that MG1-688432 is not a single star. It is, in fact, a member of a binary system. The companion is thus far unobserved. The period of 6.6 days is correct. The K3 star is chromospherically active, and the spectrum is variable and quite peculiar. There is really something strange going on in this star. So there was a lot of discussion about potential models for what could give rise to these features. And the first model was that, well, the K3 star is chromospherically active, and it has these enormous outbursts that are potentially caused by magnetic flux tubes breaking through and reconnecting. The problem with that a little bit is that there are features in the spectra that are inconsistent with that interpretation, or at least they are different from what one normally sees for those types of stars. The second model that was advanced is more fanciful, but pretty interesting, and is one that we think we can at least do some testing with additional photometry. And that is that the unseen companion is a high gravitational potential energy object, and it has tidally shredded a free-floating planet that has encountered the system, which has left a spray of asteroidal-type bodies in a plane that has been captured by the binary system, and that the outbursts themselves are potentially the interaction of one or the other of the stars in the orbit around the barycenter crossing a line of nodes in the plane of the debris field. And we periodically have these outbursts as asteroid-sized bodies crash into the star. And one of the things that's interesting about that is that if you think back about the duty cycle of observation here, which, given that we lose a significant part of the year because the star is behind the sun, we have diurnal variations, we have a lunar cycle that we have to contend with. The observatory is shut down in Arizona from sort of July to September for the monsoons, and then we have other weather events during the rest of the year. So if you multiply those all together, you get a duty cycle of maybe about 10% on this star. We're finding one outburst per year, which would suggest that we may actually have more like one per month occurring in the star. So a search for more outbursts of this type could be an extremely fruitful enterprise, and could be quite directly related to the models here. The other thing is, this could be there could be a hybrid of these models to explain the star. There's both of these things could be happening simultaneously. And there's a tantalizing little piece of evidence that that might in fact be true. It turns out that a couple of months there was another test data release, and one of their postage stamps happened to lay over MG1-688432. And in 1 month of observing, they found an outburst. And this one, however, looks very much more like you expect a traditional cool star flare. It's got a very steep, slow decay, has a duration of about 2 or 3 hours, where most of the outbursts we're seeing are more like 6 to 12 hours, with this structure reminiscent of several collisions. So what we'd really like to do is ramp up an intensive program of photometry again. We'd like to find out whether the outbursts, frequency of the outbursts is evolving. There's some indication that that may be true. Is the character of the outbursts changing? And we're particularly interested in that sizzling around the outbursts, which might be smaller blocks of material raining down on a star. what is the nature of that flickering? Are there distinct outburst morphologies? Are these steep rise, slow fall outbursts or flares one type of event, and the other highly structured outbursts a different type of event? The other thing that we'd really be interested in doing, in addition to traditional photometry, is we'd like to get some photopolarimetry. It's quite possible that this could be a fairly highly polarized object, and it would be interesting to know if that's true, and then if it is, it would be interesting to see how it evolves with time. So basically, I'd like to extend an invitation to you folks, or people that you know who might be interested, to contact us. And we'd like to have you join us for our next observing season on MG1-688432. We'd like to have you become a co-author on our next paper, which we hope sheds considerably more light on this star. So I have my contact information here, and better yet, find me here at the meeting. And I will close this and open for questions with just one comment. For those of you who are interested in spectra of cool stars, from G to C type stars, of the whole range of luminosities, we have an atlas, an annotated atlas of these cool star spectra, 75 MK standard stars, with indications of the nature and use of all the spectral lines. So if you'd like to acquire one of those, see me sometime at the meeting here. And with that, I will open for questions.
Eric, did you guys consider the model of the companion star being a magnetic neutron star with its magnetic, or its beam occasionally sweeping across its companion and disrupting its chromosphere and causing it to have eruptive events?
The short answer is yes. And in fact, we considered several models. At one point, we thought we might have a microquasar. At another point, we thought we might have a black hole, stellar black hole. The thinking at the moment, and it is not very rigidly fixed, is that it could be a white dwarf. It seems very likely that it is a collapsed high-density star. We really see no evidence for the companion at all in the spectra. And that's one of the things that is a very open question at the moment. And I think it's going to take a lot more observation to sort out what we'd really like to do. We have an opportunity to get some shell spectra at McDonald Observatory, which will probably be done this year. I suspect what we really need is 10-meter time with shell spectra.
Have you looked for radio time?
We've talked about it. We haven't actively looked for it yet, but that's an important issue. The other thing that's also important is we'd like to see if we can find some X-ray data. But both of those, you're absolutely correct. Those are very important pieces of data.
Could the distribution of the outbursts in phase that you showed on an earlier plot be related to an object passing through a debris disk or an orbit?
I'm sorry, I missed the last part of that.
Could it be related to one of the objects passing through a debris disk on its orbit twice and impacting twice per phase?
That's the thought.
Right.
And the other thought is that the modulation, the sinusoidal modulation in the star, could also be a result of the star going through that Decca disk. And that's part of the reason this question of dust signatures becomes very important to us. It's interesting, the spectral energy distribution we have right now stops just to the blue of where you would like to be looking for an infrared excess. So infrared observations are something that we really need to keep an eye out for this as well. Thank you.
Okay, we have, I'm going to ask Jessica Draper online, Jessica, and ask your question.
Hi, yes, I had a question about the long-term photometric observations that you showed in the beginning of the presentation, where there were 9 or 12 years of them. There were a couple years where it looked like there was no outburst. So do you think that you were just missing the eclipse if it is an eclipsing binary, or could that maybe be evidence that it's not an eclipsing binary?
Yeah, that's a very good question. You'll notice in this distribution that there are a couple of years missing. We actually had 2 years in 2015 and 2016 where we were just completely knocked offline by weather. So that's the discontinuity there. There are a couple of years where we did not see a very large outbursts, and I suspect that that's just an accident of timing of the observations. The only way to determine whether there's some statistical significance to that is get more observations capture more of these outbursts. And the thing that actually, I took one of the slides out. One of the other things that is interesting about the long-term photometry is that we see from the discovery data, 2001, to the time when we started making, just about the time we started doing follow-up observations, there was a decline in brightness of the star. We have a few data points from Catalina Sky Survey where they sort of serendipitously caught this star. And you can put a pretty nice curve through the long period light curve, the long-term light curve. And you can see that the brightness has declined, but it's leveled off on a plateau now at about B14.5, something of that sort. And it will be very interesting to see what happens with the longer-term variation. Does it come back up in brightness as a supposed debris disk dissipates and the star starts to return toward its normal apparent luminosity? Or does it continue to get fainter for what reasons?
Very interesting, thank you.
Thank you, Jessica. We also in the chat have a question from Tom Smith that I think is perfectly answered by the slide here, but what is the magnitude of the system? Maybe what band is it?
In V band, it's roughly 2.5, but it's a red star. And it gets more red toward minimum by a couple of tenths of a magnitude.
I'm bringing up your email address here because the next one is, can I run the video? Thank you. Can I purchase Eric's offer online and PayPal? Can he contact you via email together?
Just get in touch with me and I'll arrange to.
Thank you.
So my email or my phone number, I can do it.
Ron, Ron, if you put your hand back up, I can unmute you to ask if you want to. Good. Yeah. Okay.
Constellation. What is that? It's at about +3 degrees, 18 minutes, and it is a indoor object. We start observing it typically in October or November. The right ascension is 12 hours, 23 minutes.
Could we go back to the TESS light curve?
Yes.
You made reference to the stars sizzling. There's a gang of us have been doing spectroscopy of stellar flares, and we call it burbling.
No, that's a perfectly fine term.
But I mean, the shape of this is exactly what we're seeing. And notice it comes across, goes up in the flare and fades down, but it never got back to normal.
Right.
And we see that too.
Yeah. Yeah, which suggests to me that that type of flaring activity that you're looking at does occur in this star. And within our group, we've started differentiating between a flare and an outburst. And it's been based essentially on duration of event, amplitude of the event, and morphology of the event. And I have no idea whether it's correct or not.
Outbursts go on for
Hours and hours and hours, maybe a day.
Oh, thank you, Eric.
Thank you.